Okay, we're back.
Yay,
Yay.
we're back. So what else? What else do you want to know?
What else do I want to know? That's a good question.
I'll pretend to have all the answers.
Okay, how about if we do a thought experiment? Do you like thought
I
experiments?
love thought experiments.
Can I give you a fun thought experiment?
Give me a fun
Okay.
thought experiment.
What if space is really not expanding? Oh, wouldn't that be neat if all of a sudden we found out today that space was not expanding? That was just illusion.
It was an
What
illusion.
would that mean? That would mean we'd have to use Einstein's cosmological constant, wouldn't it?
Well, right. So we would have to fine-tune things in such a way so the universe wouldn't be expanding. But you see, if the universe weren't expanding, then we have to explain why every observation we've done to date suggests it is, and it's expanding at the same rate. And that's very difficult to do. And so people try to do that, right? So people try to say, maybe there is no cosmological constant at all. Maybe what happens is that Einstein's equations, his theory of general relativity, is wrong. So what do? They add new terms to the Einstein equations that perhaps suggest that the universe is not expanding today. But then you have to make sure that you can still explain everything else we've observed. And typically, that's when these theories come into trouble. They cannot explain simultaneously everything we have observed. If they try, then they are led back to Einstein's theory of general relativity with a tiny cosmological constant.
Right.
So that sort of blows your mind. It's like we are trying to force the universe to behave like we want it to behave, and the universe is saying, no, I know what I want to do, and you just have not come up with the right answer yet, with the right explanation.
So let me play devil's advocate here a second.
Let's do it.
That's a fun game, isn't it?
I love it.
Okay, so let's say the redshift. Okay, let's come up with this theory. It says, as a photon travels through space, as space expands, it increases its wavelength at redshifts. So I'm going to come up with a thought experiment here. What if, as a photon travels through time, their energy levels decay by 1 Planck constant approximately every 32 million years?
That's a very precise thought experiment you have there.
Isn't that? Now, let's play this out a second. So as the photons travel through time, their energy levels decay.
Mm-hmm.
What if that's what's really going on with this?
Yeah,
Come on, that's big.
perfectly fine. Yeah, but then you also have to explain the cosmic microwave background, and you can't. You can't, because these points on the sky, they have to be at exactly the same temperature.
What if the microwave cosmic background is simply the temperature of local space, and that it isn't redshifted?
Well, but it's not just that it's. If in order for it to be the temperature of local space, then every point in local space needs to agree that it's the temperature of local space. Right?
But what if it's just reflected energy from the sun?
No, it can't be that.
Why
There
not?
wouldn't be not enough power for that. We can observe. So the sun has nothing to do, say, with a cosmic microwave background. This is observed by like looking at light that was emitted billions of billion of years ago. So the sun and the solar system are completely irrelevant. In fact, if you try to observe the cosmic microwave background and the sun is in the way, you sort of have to remove it, right? Because the sun is this magnificent source of light, and it sort of completely blocks any other background radiations. In fact, you have to look for this thing, this cosmic microwave background, precisely where there is no light.
No.
And that's what causes all these difficulties. People have played these games that, maybe Newtonian gravity is right, and all you need to do is change the frequency of light. But if that were the case, we would not be able to explain gravitational waves. We would not be able to explain the global positioning system. We would not be able to explain the merging of black holes. We would not be able to explain observations of light that is emitted when matter falls into the center of the Milky Way. Did you know that there is a supermassive black hole at the center of the Milky Way?
Yep. You told me last time you were here.
I did. And so it's not just you have to explain one or two things. You have to explain a plethora of observations. And that's what's so hard, especially when the observations become more and more precise with time.
But that's where my thought is, my experiment thought. Okay, think about it. As a photon travels through time, and all that's happening is that as energy levels are decaying, what's going to happen to its frequency?
But why would they be decaying?
Huh?
Why would light be decaying as it travels through time?
Maybe in our next radio broadcast we could talk about the
Here's
cosmic trolls that are stealing the photon's energy.
But here's what a physicist would say. That's a great idea. Let's test it.
Okay.
Let's set up a cavity where I bounce light back and forth. Let's see if its frequency changes with time.
But you'd have to, in my theory, you'd have to run it for 32 million years before it would decay. One Planck constant.
Okay, so let's assume that that's right. Then how does this theory explain black holes and neutron stars and the CMB? I got you.
Yeah, you got me.
So typically what we're trying to do is come up with a single explanation that matches all observations. You can, of course, come up with many explanations that match different observations. Like, for example, you can say, well, this particular observation of the orbit of Mercury can be explained in this particular way. And this observation of light that got emitted by stars that graze the sun, bend the light from the sun, that was produced by this other effect. But in some sense, that's not very satisfactory because you're coming up with completely disjointed ideas to explain different things you observe. The ideal would be to come up with a single framework that explains it all.
Mm-hmm.
Occam's razor, right? Like the simplest explanation that covers everything is probably the one that ends up being right. That doesn't mean that other more complicated explanations may not be right. Maybe they are right. And the only way to tell is to do experiments, to come up with new, more precise experiments. Maybe your light experiment could be tested. Maybe you don't have to wait 32,000 years for light to decay. Maybe it's a continuous thing. Maybe you just wait 10 years and maybe it won't decay by a lot, but if you have a precise enough instrument, you can see the tiny, tiny, tiny change, and we don't.
But maybe this is proof that photons decay in energy. Think about that. How do you...
Perhaps.
Well, let's think about that. So Hubble saw light redshift about every 32 million light years, right?
Something like that.
Something like 10 parsecs or something like that.
Mm-hmm.
So that's where I came up with that number, 32 million.
Mm-hmm.
And so what if a photon's going through time and every 32 million years it just decays?
Discretely,
Isn't that a great idea? Is that crazy?
It would be a fascinating idea. We would have to come up with a model to embed it in everything else we know and then test it.
Well,
if you can't test your idea, then it's not a very good idea. Right?
Well,
for a physicist,
first of all,
a physicist wants to be proved wrong.
Yeah, but first of all, if this was right, it means we'd have to recalculate everything, right?
Right, and I bet you that there's very simple measurements that we can do that could not be explained by this particular effect. So, for example, the orbit of Mercury has nothing to do with light per se. It has to do with the motion of a planet around the sun, and that requires general relativity. And general relativity by itself has this effect sort of embedded in it. So you can say, well, in addition to general relativity, which we know we need because of Mercury, maybe this other thing is also happening simultaneously. And then there's this admixture of effects that you're observing. But then I would argue, okay, we also know that light gets deflected when it travels near the sun, and this can't explain that either, this redshifting phenomena, right?
I don't know. This is fun stuff to talk about, isn't it?
It is, absolutely. And this is what we do at conferences. We think about what could be explaining the acceleration of the universe. You know, what ideas, clearly the ideas we have had so far have not been able to satisfactorily explain. I mean, you can always argue the cosmological constant is just a constant of nature, like the acceleration due to gravity, you know, or like Planck's constant, or like any of these other constants that we use in physics. Maybe it's a fundamental constant of nature. It is just there. But the fact that it's so close to zero makes you wonder a little bit. Constants, if you were to pick a random number in nature, it would not be zero.
No.
The probability of it being zero is infinitesimally small. If you pick a number, it's going to be some number, right? And the fact that this number that we measure is so close to zero indicates typically in physics that there's something special happening that we don't understand. That's why everyone's so excited. And it's something that's in principle at our grasp. It's something that we can in principle understand in the next 5 to 10 years. So I think cosmology is getting really exciting, really, really exciting. Understanding the CMB, understanding the late time acceleration of the universe. This is where the next big discoveries, in my opinion, are going to come from. Gravitational waves, I think one could argue, by far the most important discovery in 2016 and 2017, perhaps even this entire decade. Especially, of course, I would say that because that's what I study. Yeah. For me, of course, this discovery is really special. But if you start thinking, what else is out there that we don't understand? Well, this cosmology is something we don't really understand very well. And there's a lot of moving parts. And if you change one, then the whole edifice collapses. And so, stay tuned. It's going to be really interesting.
And this is where I'm going with this, is that, we think that light can travel billions of years and never lose any energy. What if there's drag in the universe, in space? And light does. It's an intrinsic value in light that it does.
But if you want, that's exactly what Einstein's theory predicts. This drag that you're talking about is being sourced by the stretching of space.
We'll be right back.